Alright guys, so this is a 400 horsepower electric motor. It's got a little grounding brush right here on the shaft, and that's going to protect that bearing from shaft currents. You get build-up voltage inside of that thing, it arcs through those bearings, destroys them pretty quickly. Now, we've never done business with this company. This motor is grounded, but word on the street is they can't get one of these things to last more than 7 months. So we're going to seize this opportunity to take this thing apart, see why it failed, and then ultimately we're going to have to fix it. So we're obviously going to start with removing all of these shaft attachments, this key stock. We're going to remove all of our end bell bolts, bearing retainer bolts. We got our opposite drive end bell off. And just from this perspective, the winding doesn't look in too bad of shape. It doesn't look like it failed, but looks can be deceiving. We also have to get the other side open. It does have thermal overloads in it. And now that we got our drive end off, we can get another view of this side of the winding, but you can see there's definitely a color variation in this drive end side compared to our opposite drive end side. Now, there's an old saying that every 10 degrees C we operate this thing over temperature, we're going to decrease our winding life by half. That means if this is a 10-year motor, it's now going to be a 5-year motor, and every 10 degrees C we operated over that, we half that half. So if it was a 10-year motor, that's now a 5-year motor. 10 degrees C over that, it's now a 2.5-year motor. Again, with that color variation, you can actually see our phase paper on this side is more of a white amber color from that varnish and insulation, but you can hear all of these top sticks are just breaking and crumbling from overheating. This insulation system is totally broken down. On our opposite drive end that doesn't seem too hot, they're kind of flexible. They're still rigid, but they're pliable. They're not breaking. Now I'm going to pass my camera through the bore of this electric motor, so again, you can see that color variation and just this broken down insulation system on our drive end. That means we have to rewind this, so we're going to have to pull all of these wires out. We're going to count them, measure gauges, things like that, but the first thing I'm going to need to do is cut this old winding off, and I normally do this with just an air chisel like this. We get these different tips that you can use on these. We'll press that nice and tight up against the coil, we'll run some air through it, and it'll chisel right through those coils. They do make tons of different cutoff saws and different things you can use to cut these windings off, and we do have one. However, I think it's a little bit too small for something this large, but I've gotten pretty good at using that air chisel, and I can cut these pretty clean without damaging that stack. We do not want to cause damage to that laminated iron core. After we've got that one side cut off, we can stick this in a burnout oven. This is another way that we get these things to look nice after they've been painted, because we can sandblast this and that paint will just fall right off. Now, they are looking to get this thing back pretty quick, so I'm going to start stripping it, even though it's actually about 320 degrees Fahrenheit, which is pretty warm. We're going to wear some gloves and we'll dig through it. We're going to take some measurements with a tape measure, just seeing how long these coil extensions are, how wide they are. We want to make sure this all fits back the same way that we took it out. Now we need to see how our internal connection was done, because if we connect this wrong, we're going to have problems. It's not going to run properly. We're not going to have the same performance. So our lead comes in here. You can see that sleeving, and then it runs down here and goes right into that coil. So these leads are what are going to our line power, and ultimately this one was being ran as a 2-circuit delta, because we have 1 coil end per lead, but they're terminated as 4 to a line, so this is going to be a 2 delta. Now we braze all of our internal connections, but we're going to pull this back because I want to show you this magnet wire that runs in here. So we have our lead and then we have our sleeving. There's a connection right under that sleeving that's going to join that magnet wire to our lead. We also need to see how many wires it was wound with. So if we cut that open, now we can see our lead wire comes into here, and they actually crimped this onto our magnet wire, and that's what's going up and making up our coil. And there are 30 wires, so we're going to have to set up 30 buckets of wire, and every time we spin one of those, it's going to add 30 wires to that coil. So we also need to count the turns of that coil. So when we pull that coil out, we're going to divide whatever we count by 30, because that's how many wires it was wound with. And not to spoil it or anything, but it was 90 wires per coil, which is going to be 3 turns. It's also a good idea to count multiple coils in these larger motors, because they might do offset turns. 3 turns, 4 turns, 3 turns, 4 turns, and a 3 sitting on top of a 4. So you have 7 turns per slot. We also need to get a micrometer and measure the gauge of each one of these wires, because they will mix match different wires to come up with different circular mils per amp to be able to carry the current that's going through that coil. Now, because this is a 2-circuit delta and it's not maxed out, being that it's a 4-pole, we could switch it to a 4-circuit delta. And what option does that give us? That gives me the option to reduce the wires in hand, or the 30 buckets that I'd have to set up. I could set up 15 buckets, do 2 times the amount of turns, and then I can double the circuits. What's the problem there? I like to use ESA's redesign and verification program, so as a 2 delta, we're looking at about 38.3 volts per coil. But if I switch this over to a 4 delta, we're going to have 76.7 volts per coil. Now that's not exceedingly high, but it is something to note. You might want to insulate mid-group, because we're going to have higher voltage stress between our coils, even in that same group of coils. Now I'll start pulling all of these coils out, and again, we're going to count these. We have to note those turns and make sure that we don't have uneven turns throughout that group. I know some people like to wake up and they go through that ice bath, but I just pour a little bit of water on this winding and I get a little sauna action going. But I actually do that just to keep the dust down. We don't want to breathe this in, and you do want to be wearing a mask whenever you are stripping these things. Tech tip number 34, when you're stripping these things, make sure you are taking care not to bend any of those laminated teeth up. This is probably one of my biggest pet peeves, is any of those teeth being bent upward. You have to try to bend them back down. When we sandblast it, you get sand in beneath them, and they never sit back the way they are, and any of those air gaps are just going to cause issues with efficiency. Now, if you aren't already, I hope you guys are hitting that follow button, subscribe. Check out isa.com if you want to see some cool electrical information, or maybe if you're looking for a career in electric motors. Cheers, guys.